starting now, so everything is going to be recorded at this point. All right, so today, we're going to start with a question-answer, approach, because Lupe, sent a whole bunch of questions, and I was just basically, trying to answer all of those questions to my best ability. Not just me. I actually did a lot of research, and that's why we see, these footnotes, right? The footnotes are basically the link to the relevant documentation. All right, so I am going to zoom in a little bit, because
I'm sorry, I
otherwise,
didn't get a chance to look at this today.
that's
Where
fine.
did Lupe write his questions? Did he do it in the chat that we have?
No, no, he sent those questions to me directly.
Oh, okay. And you're going to
Um,
go over those in class with all of us? Okay.
Exactly. So,
Okay.
so we're just basically going through all the questions, and then I'll go through the answers. Some of
Okay.
these are have shorter answers, and some have long answers. So, we'll see how that goes today. All right. So the first question is there some sort of formula for determining how much space to allocate when creating a dataset? Example, I am setting up a sequential dataset containing the 50 states. How do I determine when to use blocks, tracks, cylinders, kilobytes, megabytes, bytes, or records, and how many of those?
This is a good question. I have been wondering this too. Thank you for putting it in words, Lupe.
Yeah, so I did some research. Remember, I'm not an IBM practitioner, but I can understand the concepts. So as far as I can figure out, the answer is kind of long because I want to give you guys the background first, and then we'll talk about the actual answer in a few sections. All right, so the background is a comparison of the file system of basically a modern operating system. Linux is basically the basis of Android. Mac OS is based on Unix. So these two really kind of belong together, except Apple has its own file system, so it's not using the usual Unix file system. Windows has a really kind of modern type of file system as well. We call it NTFS. Um, so unlike those file systems, a dataset is meant to be organized by hardware parameters. So what I mean by that is when we create a dataset, the creation parameters, has to is associated with the hardware geometry of a DASD or a tape drive or something like that. That is not the case in other file systems. So in Windows, when you say, "Oh, I need to create a file, to store my, let's say Microsoft Word document," when was the last time that you had to specify, "Oh, I need this many cylinders, or I need this many tracks, or I need to pre-allocate this many kilobytes or megabytes, for this particular document"? You simply don't, right? I mean, you just say, "Oh, here's a document, save it," and that's it, right? You don't have to do the pre-allocation. Um, Extension 4 is a Linux file system. Same deal. Okay, even though there are major differences between all of these, file systems, and I think with Mac OS, it uses HFS, high performance file system. Okay, something that's also different. But all of these file systems they do not require you to specify, oh, what is the largest size you can store, where should I put this, how many tracks, how many cylinders, and so on. You simply do not need to enter all of that data to create a file. Um, and then most of the file systems allocate by small block sizes. So, it depends on the disk geometry, but most file systems that I have just mentioned, they would allocate in blocks of 512 bytes, which is basically half a kilobyte, to maybe 4 to 8 kilobytes. Now that is parameterized. When you format a drive to NTFS, you can actually specify what is a block size, but typically it is ranging from half a kilobyte to maybe 8 kilobytes or so. You can make it larger, but it's really kind of unusual that people would make it any bigger than 4K. All right, so now the question is why, right? So why, is ZOS going to approaching this in an entirely different way. Um, so the method used by the other file systems is very storage efficient for small and large files, especially when you have a lot of smaller files. Because the allocation size is in increments of half a kilobyte. So that means if you have a file that has, let's say, 42 kilobytes, um, your utilization of actual disk capacity is really high, because you're not leaving a lot of stuff to waste. And that really kind of brings back the point of when you're dealing with a PC, a personal computer, or Android, or something like that, most files they tend to be fairly small by comparison to what a mainframe dataset may look like. Um, Now, obviously, if you have a file that only has one single byte, and because each allocation block has at least 512 bytes, so in that case, obviously, your waste percentage is really high. But the other consideration is, yeah, so you're wasting half a kilobyte, almost half a kilobyte. It's not a big deal because your drive has typically terabytes now. So that means, this kind of, wasting, when you have a tiny little file, which doesn't occur very often, is negligible in the grand scheme of things. So the problem with this type of file block allocation, when I say this kind of block allocation, I'm referring to allocating half a kilobyte of a block, or maybe even up to 4 kilobytes of a block, is as the file gets larger, the file system will need to allocate more blocks to store the content of the file, and then the file system will also need to track which logical portion of the file is living where on an actual physical storage device. Now, this is not really a problem by itself, but all that means is your file is not in one contiguous area. It can be scattered all over the drive. And as a result, the tracking part is not a problem, because modern file systems typically use what we call a tree type data structure to keep track of where those sectors or where those blocks are located. So this is a really efficient way of keeping track of how do we string all of those 4 kilobyte blocks together to form a file. So it's not a big problem. The real problem has to do with access time. um, so the access time is a big deal because if you're using a traditional hard drive and your file is broken up into tiny little pieces and they're all over the disk, then every single time you want to continue to read a file to the next block, your hard drive is going to have to seek. It has to move the disk head and also wait for the rotational delay. So those two items, add up to a lot of delay or latency when you're trying to just sequentially access a file. Now, in our case, okay, when we're thinking about NTFS, on your desktop computer, or when we're thinking about a file in Android, on your mobile device, if you have to wait a quarter of a second, to access the entire file, it's not a big deal, okay, because it's just an end user kind of thing, and a quarter of a second to us is not really that big of a deal. But on the other hand, if you're trying to handle a large amount of data processing and there's a lot of stuff going on and you absolutely have to get things done by a certain time, like getting social security checks printed by a certain time so that they will be sent in time, so that people can get their social security checks, to and spend money on essential items. So in that case, we cannot just go like, oh yeah, it might take a little bit longer. No, that is not really an option. So that really is the reason why a dataset is not allocated the same way that we normally allocate a file on a desktop computer, on a mobile device, or something like that, because it really needs that extra efficiency. All right, so are we doing okay so far with the background? Which is really just trying to explain why input output efficiency and performance is is a key factor when it comes to data processing with mainframe computers. It's not as much of a factor when it comes to a personal computer or personal device. Are we good with that?
Yes.
All right, cool. So the next section talks specifically about dataset allocation. So dataset allocation is always done by what they call extents. So footnote number one, links to that particular discussion of what an extent is. So essentially, what an extent is it is called a contiguous, and I put it in double quotes because the concept of quote unquote contiguous, is changing. So, I put it in double quotes. An extent is a contiguous region on the device. In the case of a hard disk drive, these would be tracks of the same cylinder, and typically they would be, it would be tracks that are in the same sequence, like track 0, track 1, track 2, instead of jumping around in different tracks. Technically speaking, if ZOS has to allocate in, like not exactly the neighboring track, but they're all in the same cylinder, physically it does not cost anything extra because all the tracks can be read at exactly the same time, so it doesn't really incur any extra time. But it does make allocation and tracking, which track is already allocated, it does make that portion a little bit more difficult. So I'm not 100% sure whether the tracks have to be adjacent to each other or whether they just have to be in the same cylinder. That part I do not know. Okay, I'm suspecting they have to be adjacent tracks. So the idea is sequential high-speed access of an extent. That is how we minimize the access latency, especially when you're dealing with a mechanical hard drive, because in a mechanical hard drive, um, if you don't need to seek, okay, if you don't need to move the disk head, and all you need to do is to read the multiple surfaces of the platters of exactly the same track position, that doesn't take any extra time, okay, because reading one track versus reading all the tracks of the same cylinder takes the same amount of time. Now, that is given the input output controller is capable of reading multiple tracks all at the same time. And I suspect, in the case of a mainframe hardware, that would be possible. It just doesn't make sense that that would not be possible. So tracks of the same cylinder can all be read simultaneously without incurring any extra overhead of seek time. So that is the whole reason. This is the whole reason of why they use the concept of an extent. Okay, so basically everything within the same extent, they can be accessed sequentially with very little latency. When the dataset is first created, it would be created with a primary extent. That part is specified by space, by the space parameter of the allocate command. And here we have another footnote number 2, and that refers to the space parameter. The space parameter allows you to specify two things. The first one is how big is the primary extent, and then the second one is how big is each secondary extent. And they can be different. They don't have to be the same, and most of the time they are not the same. The primary extent probably should be large enough to accommodate what you consider is what you would expect to be the size of the data set, because you want everything to be within the same extent in order to maximize the efficiency to access everything. But if that is not possible, like if the data set is potentially can be grown over time, then you also have to specify something for the secondary extent size. So when you run out of space in the primary extent, and there's only one primary extent to each data set, once you run out, then you have to allocate in units of secondary extents. So now you have to allocate, you start with one secondary extent, and when you use that up to, then you have to allocate a second secondary extent, and so on. So when you specify the size of a secondary extent, you have to take into consideration, are you going to waste a lot of space? I mean, sure, you can make the secondary extent just as large as the primary extent, but if the chances of filling up that space is really slim, and you're thinking, oh, I might be over by just 2 or 3% of the primary extent, then you don't really want to use the size of the primary extent as the size of your secondary extent. You might want to use a small fraction of that, so that way if you do allocate secondary extent, you'll just be allocating secondary extents as needed on demand, and instead of pre-allocating a big chunk only to find out that, oh, we're not using 75% of that secondary extent. So that's the reason why we have primary and secondary extents. And the consideration of the sizes of the extents depends a lot on the data set, and also what you anticipate to be to be the range of the size or the length of the data set. If you don't really expect things to change a lot, and you think the primary extent is already large enough, you can just make the secondary extent a fairly small value compared to the primary extent, because it's just a just in case kind of thing, right? On the other hand, if you say, well, I know the data set is kind of small right now, but over the next several months, this is going to grow, and I know this is going to grow by a lot, then you might want to allocate the secondary extent to be fairly large too, because you already know that it's going to grow. Does that make sense so far? Does everybody understand the
I
concepts?
understand the concept about the primary extent and the secondary extent. What I don't understand is how what you're going to select it to be as like in blocks, tracks, or cylinders.
Okay, we'll get to that.
Okay.
We'll
Same
get to
here.
that. Yep, there's more stuff coming. Okay, so the next paragraph talks about the term of a block. Okay, so a block is not necessarily a logical record. So a logical record is, from the perspective of a COBOL program, or from the perspective of a job, a a logical record is the smallest unit you can process that you can read or write from the perspective of a job. But a block is not necessarily a logical record or the size of a logical record. The relationship of how the size of a block relates to the logical records in a dataset depends on the type of the dataset. And here we have footnote number 4 that goes into more details. If you look at footnote number 4, it actually outlines the different types of record formats, RECFMT, RECFM, um, and indicate how the block size relate to records. Although it is not stated, so this is my speculation, a block is likely to refer to the amount of data transferred to each input-output operation between the ZOS operating system and the device. So a logical record is how much data do we process. Um, it's the quantum of how much data we process from the perspective of software. A block size, on the other hand, is determining how big of a chunk of data do we read and write each time when the operating system is interacting with the input-output device. So these two are different because you can, if you want to, with a I'm trying to remember the name, with a BSAM. Okay, so with a BSAM, which is a basic sequential access method, with a BSAM dataset, it is required that your block size has to be coinciding to be exactly the same as a logical record size. They have to be exactly the same. So in that case, you will be, and if you're reading a lot of records, then you have a lot of overhead, because in order for the operating system to talk to the input-output device to read something, there's a certain amount of overhead associated with that communication. So if you need to do that communication for every single record that needs to be processed, that's a lot of overhead. On the other hand, if you use QSAM, which is queued sequential access method, for a data set, then you can group a whole bunch of logical records into one single block, which basically means you don't have to worry about that part. Okay, it is up to the operating system. There's a separate question that addresses that part. So it's up to ZOS to handle that part. All you do is I need to read the next record, the next record, the next record. But the operating system, understanding that you're dealing with QSAM instead of BSAM, will basically read a chunk of data. So it is only using the overhead of interacting with the input output device once, and then you will be reading a whole bunch of records at the same time. Now the job doesn't know that. The job just said, "Oh, give me the next record." But the operating system is buffering a whole bunch of records that is invisible to the job at the time. So it's very quick for the operating system to go like, "Oh, here's the next record, here's the next record, here's the next record," because they're all already read in memory. And then after you process all the records within the same block, and then you ask for the next record, the operating system knows, oh, okay, I need to go back to the IO device to grab the next block. So it is a lot more efficient that way, to use a QSAM type of data set instead of a BSAM kind of data set. um, All right, so we are down to here. A large block size has time efficiency when records are accessed sequentially. So this relates to whether something is sequentially accessed or not. Now, most data sets are intended to be accessed sequentially. Now, IBM does have data sets that are not sequential. Like VSAM, has the ability to kind of jump around, and quote unquote random access. But for the most part, I don't work for the state, but I'm guessing most of the data sets are sequential. So I'm gonna ask you guys, do you know whether sequential data sets is the usual, and then the indexed um, um, data sets are the kind of like the rare cases? Is that true?
Yes. Is that what you're talking about? The cluster?
Yeah. So what I'm asking is, as far as are most data sets, that a data center process, are they sequential in nature or are they indexed in nature? In other words, are you expected to random access the records within a data set, or do you read most of all the data set in a sequential order?
Some are random access, but I'm not sure which is more, sequential or random. Uh,
Okay.
what I know, like basing on my training,
Mm-hmm.
um, we have requesters where, because we deal with a lot of pink slips and uh, registration stickers and stuff like that.
Mm-hmm.
So let's say, for example, we have a customer who really needs a copy of their title for their car because they need to sell it,
Mm-hmm.
right? So we will receive a request to randomly access where that pink slip is or the
Okay.
title record in this big dataset file,
Mm-hmm.
right? Or dataset. And so we go in there and we would just type in the license plate number or the VIN of the vehicle,
Mm-hmm.
and the computer tells us directly what data set that is, where to find it.
Okay.
And then
Yeah. Go ahead.
so there will be a day where, okay, this is the day, because you know how we ran the titles. Let's say they requested it, but it doesn't really take like they can't just go to the field office sometimes to
Mm-hmm.
pick it up, right? So the pink slips come from the headquarters. You don't. It doesn't come from the field offices. They don't issue the pink slips there.
Mm-hmm.
So it will take time for them to get it. So we have a 72-hour special. I don't know if I'm getting out of the topic, but the 72-hour special makes us randomly go in the system and find that specific record and print that uh, pink slip right there, and the person comes in
Mm-hmm.
at the gate and picks it up, and
Mm-hmm.
we will be able to handle it right
Okay.
there and give it to the customer.
Mm-hmm.
So I guess most of the time we have random access as well. I don't know if that is that what your question is, or
Well, so what you told me is you have interactive access, to the
right.
data, but I don't even know whether the data is really stored in a data set or whether it's stored in a database. Remember the discussion from Monday that
That
some applications rely on the database instead of storing data in individual data sets. So
they're
do you
in
know
data set.
whether the data is actually stored in data sets, or do you know whether there's a possibility that the data is actually already stored in the database?
I know for sure it's data sets.
Is data sets? Okay.
Yeah, I think what I'm getting confused here. Sorry. Uh, let's say there's 20,000 pink slips are scheduled to be printed
Mm-hmm.
today, and we found out that the pink slip that they're looking for
Mm-hmm.
is in that data set, and it's gonna be printed on at a certain hour of this day.
Mm-hmm.
So it tells us where to look exactly, where to find it and in the data set. And then we have access to the output
Mm-hmm.
during the day, and we would actually just pull it from the box.
Mm-hmm.
So it tells us which box, which data set, which everything, and we will actually pull the specific pink slip
Okay.
and put it in an envelope and give it to the customer. I don't know if that's really a random
It's
access or
hard. It is hard to say. It's hard to say, Jennifer, because I can, I was listening to you and I was running an algorithm in my head,
Mhm,
where you can have one job to go
mhm,
through every single vehicle registration and figure
mhm.
out which one which one needs to have the pink slip printed. So
Right.
so that can be sequential, because because you have to go through every single one in order to
Okay.
find out which one is it's time for it to be printed. Now,
Mhm,
that sequential process, can be sped up, depending on how frequently you have to do stuff like this. So if you can sort by date, okay, of
okay.
the vehicle, when was a vehicle last, um, so the pink slip is printed uh, when what is the trigger of the pink slip being printed? Would it be requested, or do you have a change of possession?
uh, it was requested,
Okay,
by there's a work order, or they would call
okay,
they'll call it in.
okay,
It's a special processing that we do.
okay,
Uh, they pay extra for it, but
okay. So I can
yeah.
see how the requests are stored in its own dataset, and it can be sequential. And
Okay.
what the system is going to do is it will basically be going through. It will have to sort the dataset representing all the requests, and it also
Mhm.
has to sort all the vehicle registration. Also by the same key. Okay, so let's say each vehicle has a VIN, right? So we can
Right.
sort it by the VIN. So then so you have, okay, the camera is important in this case. So you can now scan the two data sets. You can scan the request and locate a particular item, and then the other one will kind of sequentially also scan until it has a match of these two, and then you have just retrieved the data of the vehicle that needs to have a pink slip printed. Then you output that to a third data set, which is the output. So
Mhm.
basically, for each data set, it only has to be accessed sequentially. It sounds really kind of tedious, right? Because you're gonna have to go through the entire data set on both ends.
Right.
Um, but that's what mainframe computers were built to do. this
But
is
it
what
was
this
really
is
fast, though. I mean, you could access something really fast.
Yes.
Right?
It can, and this is the amazing part of mainframe computers is something that seems to be inefficient, because we are sequentially accessing something and scanning through stuff. Um, that sounds really inefficient, but the mainframe computers actually has hardware specialized, hardware to do this kind of stuff. And this is one of the main reasons, why IBM mainframe computers are still being used is because it just has the specialization to do this type of thing in a very very efficient way. From what you told me, it doesn't really quite limit our options to it doesn't have to use indexed type of data set. You can still use sequential, and from the end user's perspective, we wouldn't be able to tell because it is so fast. Because when you're reading a data set,
Right.
multiple mainframe computers can read the same data set at the same time. When you're writing or updating, obviously only one should be able to do it. But when you're reading, multiple mainframes in the same sysplex can be reading it at the same time with the same kind of efficiency. So it doesn't really quite tell me which way the data set is organized in this way, in this situation.
Okay.
Yeah. Yeah, because a lot of the older COBOL programs were written to process only sequential data sets, because that's because in the earlier days we only got tapes, right? And before that we only got punch cards. So both of those devices are inherently sequential. There's no such thing as random access with those devices. So that means a lot of the older, COBOL programs, built from the 60s, possibly into the 70s, were built to only process, sequential data sets. Now, the chances of someone going in and go like, oh, this is not efficient, and we're going to use the indexed approach, that's always a possibility, but that also introduces a risk factor because every single time you reorganize data in the dataset and you have to change the program to access the dataset in a different way, there's always that chance that a bug is introduced into the system, and we are not talking about a simple bug in this case either. We are talking about a nasty bugs that are difficult to detect. So a lot of times, organizations like the government, credit card companies, basically the risk is too high to um, to optimize for performance. So if they can't get away with the older ways of doing things but it is known to be reliable, they will stick with the older way but not so efficient way of doing things.
Okay.
Um, so I'm
I
just
know
saying that
we
because yeah, go ahead. Sorry.
I know we use a lot of sequential. We have a lot of sequential data sets as well.
Mm-hmm.
Because I remember there's a task they gave me to compare the counts there's a record that I have to compare the total counts.
Mm-hmm.
And it says on the task, if the counts don't match, then there would be an issue. So
Mm-hmm.
you got to go in the data set,
Mm-hmm.
look at the counts that it has there, and look at your paperwork if it doesn't match. So I tried to access the data set, but it tells me it's on tape and I can't access it. So I asked my mentor, how do I access this data set? Because it's telling me that I don't have the access, it's on tape. And so my mentor came over and showed me how to request access on this tape.
Mm-hmm.
And when she showed it to me, it's not even a second. And she said, oh, they already gave you the access. It's right there.
Mm-hmm.
It's not even a split second or whatever. It's fast. It's fast. I got the access right away.
Mm-hmm.
And then I open it and it showed up, but it's on tape before. But
Mm-hmm.
now it's so efficient that I was able to access it right away using ISPF.
Mm-hmm.
And so all I'm saying is the tapes are sequential data sets, right?
Mm-hmm.
So it's really efficient as well because even though they're reading it sequentially, right? then I mean it's also fast
Yep.
because I was able to access it really
Yep.
fast. I thought I have to wait for a few minutes before I could have access to it, but it's not. It's like not even 1 second. It's there. It's they gave it. They gave me access right away.
hmm
I don't know how they transferred the information, but it was really efficient.
Yep. Yeah, I found. Uh, do you guys remember? Let me look at the date. About a year ago, in April, I think it's Colorado that has a problem with printing unemployment checks.
Oh,
You guys don't remember? Okay. So basically, they are. Um, I'll bring you the link here. I know it is slightly out of the context of this class, but I think it is really relevant to what we are talking about here. So this is the headline of unemployment checks are being held up by a coding language almost nobody knows. So they're basically blaming it on COBOL. This coding language that almost nobody knows was COBOL. And indirectly, they're pointing the finger to IBM and and they're basically telling people these are really old computers, and this is the reason why they could not print the unemployment checks. That turned out to be not true at all. That turned out to be not true because the bottleneck, what broke, when there were many people trying to log on to the website to request, to register and to let the system know that about their unemployment status. It was the front end. It was the web servers that broke. So the web servers turned out to be Microsoft products. So they were using IIS on very old platforms. So there was a hardware issue and there was a version issue because they're using very old software, and you actually have to use old versions of Internet Explorer to access that website. So that kind of tells you, the front end part was not up to date. And it was the front end that got overwhelmed. The back end, on the other hand, the mainframe computers, they were just twiddling their thumbs the whole time because they were able to process a huge amount of data, but the data was not able to come through because the front end broke. So that was it was interesting because I was with some IBM people at the time, and they were trying to they were trying to respond to all the news channels blaming everything on IBM mainframe computers and COBOL, and while the problem was not related to the backend because the backend is super efficient. Um, and the other thing that I also want to bring up, and it is related to what we are talking about, is IBM mainframe computers. I do not know of any other architecture that has this kind of construct. Is it can sort data sets in hardware. Most computers, okay, if you want to sort a file that has records, you're gonna have to write that code and use the main CP, the central processor, to do all the processing. That is not the case with a Z system. With a Z system, that can be offloaded to a subprocessor, basically, that can perform this type of sorting with very high efficiency. So they basically build the hardware around how the data is being utilized to make to make sure that all of these operations are performed with as much efficiency as possible. So that's why that is why I suspect a lot of data sets are really still sequential in nature, and they're still using older programs that use a sequential access approach or algorithm to process the data because they don't want to change how the data is organized because there's a risk involved when you try to change how the data is organized. That is considered a high risk type of operation. So that's I know it sounds unrelated to what we are currently talking about, but I think it is related in a way because once you're done with your apprenticeship, and you get into wherever you're heading, you might actually see um, uh, that um, how should I put it? You might see that tendency, okay, of people sticking with the reliable way that works instead of trying to use the newer features that is supposed to be much better, but you run into a risk of you might break code that has been known to work for decades. So that's kind of the thing that you might run into. All right. So this section here talks about to answer the original question. When a dataset is allocated using the allocate command, and there's a footnote that describes that command in great details, the space parameter specifies the number of allocation units, and the allocation units can be specified in several options. These are the ones that I found. I couldn't find byte as a allocation unit or kilobytes, so these are the only ones that I could find. Um, so it's interesting that they have a now they are not the only ones. Okay, if your system is equipped with SMS, you actually have to specify the average block size and not the block size, because when things are encrypted, because SMS stands for what? Um, I'm just looking on the side right now.
Is it system managed subsystem or system management?
Well, SMS turns out to have multiple meanings, but in the context of IBM, it is storage management subsystem.
So, okay.
It's storage management subsystem, and depending on whether that is being used and whether encryption is also used, you do not, if you're using SMS, you do not specify the exact block size. You specify the average block size in those cases. But assuming SMS is not being used, there's the block size, and the block is interesting because if you specify block as a unit of allocating space for a dataset, it is measuring the average length of blocks. So when I saw, as soon as I saw the word average, my mind just goes like, so that means blocks, the length of a block can change, because otherwise it wouldn't make sense to talk about the average. Because if every block has exactly the same length, why do we need to talk about the average? So this turns out to be an interesting discussion because it brought me to IBM devices that can handle variable block sizes, and also the IBM CKD -D organization. So we'll get into CKD in just a little bit because there was a separate question that asked specifically about CKD. So we'll deal with that later. The second one would be measured in tracks. Okay, so you can specify the space parameter. When you specify the number of what, right? As the primary extent, and also the size of the secondary extent. You can also specify in tracks. Now, if you specify in tracks, that basically means you have to know what is the capacity of a single track. I do not know IBM hardware very well, but I'm gonna guess, okay, different devices have different size or different capacity per track. So that means you are going to have to know the geometry of the DAS-D in order to use both track and cylinders. So cylinders is basically a cylinder is a collection of tracks. Basically, when the disk head position is fixed, and you spin the platters around. So all of the platters, all the surfaces of the platters, in one full rotation, makes a single cylinder. So a cylinder is basically made up of contiguous, tracks. So that's a larger unit that you can also use. Now cylinders is interesting because I may
Is
be wrong
cylinder
here.
a whole platter or a stack of platters?
A stack of platters, but it's a stack
Okay.
of platters where the I can do this. I can, I got a device today hooked up, and I can use it. All right. So let me bring it up here. No, that is not for this class. Let me see.
So a track is one rotation around a cylinder.
A
I mean,
track
around
is
a platter.
a track is one is a track is the line that a diskette would draw with one rotation.
Rotation.
Yep. but it's a single line basically on a single surface of a platter. That would be a track. But when you look at all the tracks, with all the heads at the same position, then you have a cylinder.
Oh, okay. So it's not the full platter. It's just the same
Yes,
track on every cylinder.
correct. I'm trying to. Okay, I guess I'll just use um, the same notepad. Yeah, I can move stuff around in just a little bit. So so when you look at a hard drive, okay, so a hard drive has multiple platters. I'm just gonna have 3 platters in this example. So we have platter A, platter B, and then platter C, and they're spinning around what we call a spindle. So the central axle here is called a spindle. So it's basically just rotating all the platters, around the platters are all fixed on the spindle. So when they rotate exactly the same way. So I'm just going to make the assumption that there's only one surface on each platter to store data. Typically there are 2, except for the top and the bottom, but I'm going to make the assumption that there's only one. So there's one disk head to read platter A, another disk head to read platter B, and then one more to read platter C. So these are all hooked up to the same armature, and this armature can go back and forth so that you are moving the disk head in to read the inner portion of the inner track, and you can move it out to read the outer tracks. Is that okay so far?
Yes.
All right. So assuming that this is the position of the disk head, so one track, is basically one platter, and that would be the line. If you were to draw a line using the disk head and the disk itself is rotating, that would be one track. So this is one single track. So one single track is um, a line on a single platter. But if you look
Okay.
at the collection of all the lines, on all the different platters, when the disk head is at the same position and you rotate the platters exactly in one revolution, that makes for one cylinder.
Okay.
All right, cool.
Mm-hmm.
Yeah, so I thought this may come in handy because I can draw a picture.
Okay, so what's a block?
A block is so a block is how much data you transfer every single time the operating system talks to the DASD. A block is basically how much data we are transferring each time the operating system talks to the input-output device. So a block typically would be a part of a track, but it doesn't have to be.
Okay, so it's normally just a portion of one track is a block.
Right. It depends on how big of a block you are specifying, because a block size can be huge, can be gigantic as well. So you can potentially specify a block size that can span multiple tracks.
Okay.
So a block size is a quantum of data transfer, and a track and cylinder, those relate to the geometry of a hard drive device. So those two are related, but they are not necessarily a one-to-one type of correspondence. All right. So getting back to the notes, let me put this one on the side. So you can specify by track, so you can specify by cylinder, and there's also a block size. So you can see how things can be a little bit confusing because you have block and then you have block size. But block size is the exact length of a block. So you're basically saying, okay, we are going to use exactly 512 bytes as the length of a single block. It's not an average. You cannot change it. You cannot say, sometimes it's smaller and sometimes it's larger. No, every single block is 512 bytes. So a block size is constrained by the record format operand. So depending on how you specify the record format, you need to be careful about what you specify as the block size and what you specify as the length of a logical record. I believe that is the parameter of LREC L, right? Logical record length. So block size and logical record length, there need to be a particular mathematical relationship between those two if you specify certain types of record formats. So we will talk about this in the next paragraph. Think about a record like a form, okay? A field is basically a particular part of a form. So if you're trying to fill in a form for, since we're talking about the pink slip, right? So on the pink slip, how many? Okay, let me just pull up a visual image here. Give me a second here. And see if I can pull up an image, because I think that is going to be, that makes things a lot easier to relate to. So I'm just looking up on the side to find an image of a pink slip. There we go. Okay, so let me see how I can do this. I'm gonna do it this way. I'm just taking a screenshot of a form, and I make it display in an app, and then pull that window over here. There we go. Alright, so this is a pink slip, in the state of California. So if you think about the entire pink slip as one single record, then every single field, would be referring to one logical individual item. And I can't really read that far. I mean, the details. Let me see if I can zoom in. Okay, maybe right click. Nope, I cannot zoom in, and I can't read that small. But I can zoom in with the other one. All right, so the top part here, I mean, Jennifer can probably tell me because you're familiar with these things, right? So the top part here talks about the vehicle ID number, the VIN, right? The VIN is up here. So that becomes a field of a record. And then next we have year and model. So the year is another field, model is another field, make is right here, that's another field. So you can look at if you look at a record like a form, then every individual part of the form is basically a field. So the length, the logical length of the length of a logical record now depends on how long is a VIN. Okay, if a VIN can only be up to, I'm just guessing this, okay? So if a VIN is limited to up to 32 bytes or up to 32 characters, then you have to allocate 32 characters just for the VIN. Year is probably just 4 characters, and then model, I'm not sure, I'm just going to guess, maybe 20. So you have to add up all of those, add up all the length of each field, and the total of that is going to be the length of the logical record itself. Does that make sense? Okay, all right. So that would be the first thing to determine, okay, is how big is each logical record. Now remember, when we talk about a logical record, that is how much the program, the job can read at a time, okay? That this is the smallest quantity of reading and writing from the perspective of the job. Then the next step is to choose between record format being F versus FB. FB is buffered, F is not buffered. So FB can place several records onto one single block, and then F basically specifies you only get one record per block. So that's the difference between FB versus B. It is pointed out by IBM, in the same document, but I give you a new link here, under footnote number 8. F is rarely used because it is very, very inefficient. Now, when we are back in the old days when we are processing using punch cards, okay, it doesn't make much of a difference because reading a punch card itself is the slowest operation. The overhead of data transfer between the card reader and the mainframe computer, the CP, that part is insignificant when you're dealing with punch cards. But when you're dealing with modern input-output devices like a SSD, that makes a big difference. Okay, are you accessing like only 80 bytes at a time, or are you accessing 4 kilobytes at a time? It makes a big difference in terms of the efficiency. So F is not used a whole lot, and then FB is quote unquote the de facto standard. So generally speaking, this is just my statement. This is not IBM's statement. Block size is probably the appropriate unit specifier because it directly relates to how data is stored within a dataset. Tracks and cylinders, make more sense if you're handling a gigantic, data set that needs to be sequentially accessed. Then it kind of makes sense to specify in tracks and cylinders, because in this case, you really want to make sure that things are truly contiguous. Okay, that everything stays. You can basically read everything without having to move the disk head. In other words, you want to move the disk head only once, and then you're reading everything out of the entire cylinder and process all of that stuff without having to move the disk head again. Because moving the disk head is a very slow operation, and we want to minimize that type of thing. Are we doing okay so far? With the Q&A session.
Yes, but how does it difference when you do have SMS?
So SMS adds a layer to the whole thing, and through SMS, I think it has to do with encryption. I will look it up on the side right now. So IBM SMS encryption, average block size. Okay. Alrighty. So I got something, but it's a really big document. So I'm trying to look for something that is a little bit smaller. There we go. All right, so I'm gonna bring this into this browser. There we go. Oh, it's only searching for words on the other side. Let me see. There we go. Okay, if SMS is not active, the system checks the syntax and then ignore the average record parameter. And this part talks about the average record size, determines the size of the average record block, and it is applicable only when SMS is active. So this part explains, it basically states, okay, average block or average record is only used when SMS is active, but it doesn't explain why that is the case. And I think it has to do with SMS allows encryption, and when you have encryption, then the record size cannot be fixed anymore. So that's why you can only talk about the average record size, but not the exact record size. Does that kind of make sense? Or not?
I believe everything on the mainframe is encrypted. I remember reading back where it talked about where everything is stored as encrypted, and the only time it's unencrypted is when it's actually in real memory.
I know it has the hardware to do that. I know the Z system frames, they have dedicated processors to do encryption and decryption. So you're telling me that everything is actually, so SMS is basically always on with a modern frame.
From what I understand, yes.
Okay. So in that case, none of these would matter because you can only specify the average size of a block, because you can't, because there's no way to the how data is actually stored on the physical device has the size of a record as it is actually encrypted and stored has no, you cannot control that anymore, because the encryption mechanism can change the size depending on the record itself. If you want to throw compression into it, that makes it even worse, because there's really just no way you can ahead of time, there's no way you can actually figure out. Even if you say, okay, I know from the logical record perspective, each record is 512 bytes. By the time it is stored on the drive, as physical actually bits, zeros and ones on the platter, you have no idea, exactly how many zeros and ones are needed. So in those cases, you can only specify the average record size, because the system cannot, you simply do not know how to use the actual physical device. All right. Well, that's interesting. That is interesting. So that means a lot of that means block size, cylinder, and tracks really cannot be used when SMS is enabled. Okay. All right. So shall we move on to the next question, which is related to the first one? So in reference to question number 1, because the space allocated for ZOS dataset always start at the track boundary on disk, the minimum size should be one track or multiple of tracks or cylinders. A track is 56,664 bytes for a 3390 disk device, assuming 4K blocks. Using blocks just wastes time, wastes and limits space. All right, so this is a very good question. The short answer is yes. Okay, there's no point in using blocks, because if space is allocated only by tracks, then there's no way to put two data sets on the same track. Basically, that's what this statement is saying, is one track can only belong to one data set. You cannot have two data sets sharing the same track. You cannot have, say, half the track is used by this particular data set and half the track is used by another data set. So if that statement is true, which I do not know, okay, but the IBM documentation mentions this, so that means yeah, so Lupe's observation is true. You basically boils down to it's you're allocating at least one track at a time. Now remember, your block size can also be bigger than the track, right? So that means if you specify a block size, BLK size, to be bigger than a single track, then it'll be allocating by multiple tracks in order to accommodate the block size that you're specifying. So there we go. So that means block size and space together is only making a suggestion to ZOS of how a data set to be allocated on the device. But when you use SMS, then it becomes, the whole thing becomes kind of, it becomes a moot point, okay? Because you can only specify the average size of a record in that case. All right. Question number 3. When writing JCL, is a record considered a line? And then there are two sub-questions after that. When using a continuing comma to the next line for readability, is that considered another record? And then when using a continuing comma to the next line because the command will not fit on one single line, is that also considered another record? This one has a relatively short answer. In JCL, each line is a record, and there's a footnote to refer to the IBM document that says that exactly. This means a JCL statement can span across multiple records, but it will still be the same statement. It's just that each line is a single record. So I hope this kind of clarifies that particular point. So the second portion, okay, of the answer to this question is basically saying, what if we want to integrate the data stream into the JCL stream? Okay, so there's a specific name for that. It is called in-stream data. So when you're using in-stream data, which means your JCL statement would actually specify DD as what follows. Okay, then you have the restriction. You simply cannot defeat the restriction of having a block size of 80 characters. That's it. That's all you can do. And also your logical record length is also 80 by because of using in-stream dataset. So these two, or these three, I should say, these three parameters are basically implied whenever you use in-stream dataset, and there's no way to get around it. You cannot specify a record length that exceeds 80 characters when you're using in-stream dataset. Is that kind of what you were asking, Lupe?
Yeah, the top part of it. Yeah.
Okay.
Yeah, it didn't make sense.
Okay.
Um,
Yeah, because the whole concept of a record is basically one punch card. One punch card is considered a record, back in the punch card days. But we don't see those as records anymore because now, with terminals and printers, we see a single punch card as a line, and as a result, it's just kind of, I know it's confusing because when you have a single statement, JCL statement, that has to span across multiple lines, it is still considered one statement, that has continuation across multiple lines. But technically speaking, it does consume multiple records. You're using multiple records to make one single statement. So that's kind of the bottom line. This one is more like it's more about the definition of what is a line and what is a record. And in IBM terminology, in the context of JCL, they mean exactly the same thing. A line is a record is a line.
So on an 8.5 by 11 piece of paper, one row on the paper is 80 bytes. So that's why it's the block size
Yep.
of 80, correct?
Yep.
And if your JCL statement goes beyond that, even though you use a comma for continuation, the second part of that statement is considered another record because it's on another line.
Yep, exactly. And of course, coming from my background, this is all kind of really kind of weird because in Unix and Linux, there's no such concept of a record when we're talking about basically text files, because a JCL is specified as a text file. So when we talk about text files, we only have lines. Okay, how many lines are there in this file, in the text file? But in IBM terminology, because it evolves from punch cards, so the terms are different. It's basically just a term thing. All right, so that's question number 3. Moving on to question number 4. Do you guys want a 5-minute break, or do you want to just kind of keep going? I'm good either way.
I have to use the restroom, so that would be nice.
All
I
right,
was
so
just gonna say that. So thank you, thank you,
all
Lupe.
right, we'll take a 5-minute break, and let's make it 7 minutes or so. We'll continue at 6:45.
Okay, thank you.
All right, sure, no problem. right, sounds like Carrie is back.
Yep.
Yeah, I'm actually used to teaching continuously for like 2 to 3 hours.
You do it quite well.
Yeah, just won't shut up, right? I taught CISP 300 once, as a once per week kind of class, so that became a 3-hour lecture for that class.
Was that the one on the algorithms
Yep.
that Dan taught us?
Yeah. Then Naya.
Yeah,
Yep.
that was a hard class.
Well, that's what developers need to know. And JCL has a good portion of logic stuff too, so it might be helpful to understand that stuff for JCL, to understand what the JCL um, deck is specifying.
I have a quick question while we're waiting.
Yeah, sure, absolutely.
Do you know if you're gonna be teaching the next our next two classes?
I'm
It's like,
sorry. I'm
heck no.
laughing because that topic was brought up today. The dean brought up that topic because right now we actually do not have a person lined up to teach the next two classes. So the first thing we're going to do is to talk to the JAC to see whether we can postpone the next two classes, 332 and 333. I am teaching CISP 310, which is a typical class that I normally teach over the break, over the summer break. That is usually a 4-unit class, so we are squeezing a 4-unit class into 8 weeks. So that is intensive enough for me already. Based on what I'm doing right now, which is I need to spend Thursday to kind of in the middle part of Monday to prepare enough material for the next week. There's no way I can do that, over the summer because I'm already loaded with a highly compressed class. So the answer to that question is we do not know. Most likely it is not going to be me because I am already fully loaded for the summer and also for the fall. Um, so I suggested to the dean to potentially find another instructor, who may be a retiree, like a recent retiree, because those would be very good choices. There's no work situation that can pop up anymore, right? For those for recent retiree, and yet they know everything because they have had decades of experience with this stuff too. So that's what I suggested to the dean.
Okay.
I'm not sure whether that's the answer that you guys want to hear, but right now, it's just a series of unfortunate events.
Right. I'm just curious because sometimes we don't know what to expect.
Right. I understand that uncertainty aspect of what you guys have to deal with. Um, and we didn't know either. We thought that Jerome would be teaching this class, and that turned out not to be the case. And then we thought that Sabir is going to teach the class, and that turned out not to be the case. I'm just laughing because it's a strange situation. Um, in 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 normal classes, okay, in normal classes at ARC, I have taught at ARC for 21 years. Typically, the scheduling is done a year ahead of time. So 1 year ahead of a semester, we know exactly who's going to teach which class. The only time there was an exception was one of my colleagues, who was a professor, and he was assigned as the uh, area dean, for a semester. So he had to give up all of his classes because being a dean is a full-time thing. He could not possibly teach his classes as well. So they gave me all of his classes with 72 hours, within 72 hours before the semester started. So I had to prep, basically all new classes within 72 hours for that semester. And that was also the semester when I got performance review,
Oh, wow.
which turned out to be advantageous to me because now they cannot fault me for anything. I did my best, okay? I did basically the same thing as what I'm doing with this class, except, the only exception was those few classes that I picked up from Dave. They were all stuff that I'm already familiar with. So it really is just a matter of writing everything in an order where it makes sense to the students. Whereas in this class, I understand the basic concept of, computers and architectures and files and whatnot. But IBM stuff is specific, is very, very specific, and that is new to me. And that's why I need days to look up, with tens of tabs open at the same time to put together what you guys see as text, notes. Because I have to gain an understanding of the material before I can teach that material. And that's why it's difficult for me to teach my originally assigned teaching load and pick up this class and all the also 332 and 333. When it comes to that, that became a huge teaching load for me.
Mhm.
Yep.
Well, we appreciate what you're doing. We know that you're doing a lot of research and doing your best.
Well, I'm just hoping that this relates to what you guys really need to learn, because otherwise I would just be teaching you guys a lot of stuff and none of that actually matters at work. So I don't want that to happen either. All right, so I think it's time to restart. We're actually 3 minutes past 45. All right, so this is question number 4. Question number 4 is a little bit longer because there's a little bit of concept stuff to talk about here. So ZOS treats an entire Unix file system hierarchy as a collection of datasets. Each dataset is a mountable file system, and this is awfully confusing, awfully confusing the way it is put together, the sentence. So I will try my best to answer to respond to that particular question. And these are all the text itself is coming from the reading material that I suggested on Monday. So I'm hoping that you guys have some time or will have some time to read through all that stuff. So in this context, what does it mean that each dataset is a mountable file system? Because it is actually very confusing. Okay, which file system on which operating system are we talking about? So the answer is so this link here, footnote number 12 is referring to the source document, which is one of the pages that I would like you guys to read, to establish the background, information. The source document is relating dataset, which is an IBM ZOS kind of concept, to files in a file system of Unix or Linux. And the confusion comes from the term of what is considered a file system and what mounting means in this context. So I'm going to explain 2 sentences, the actual quotes from the original text. So the first one is ZOS treats an entire Unix file system hierarchy as a collection of datasets. What that really means is each file of the Unix or in some cases Linux file system can be accessed in ZOS as a dataset. So when you specify the DD statement, there is a way for you to specify and go and basically say, oh, go to that Unix system over there. This is the path to a file in that Unix system, and treat that file in Unix as my dataset. Okay, so the DD statement allows you to do that. So that pretty much answers addresses this particular statement. The next statement is what Lupe was asking about. Each dataset is a mountable file system. What does it mean? So in an earlier answer, we learned that that a ZOS native dataset occupies extents, wherein each extent is a contiguous region on the storage device. There are also other statements preceding the quoted statement, and that particular statement that is preceding is an application reading the file, meaning the file that is on a Unix file system, is responsible for interpreting the format of the data. Okay, so that is kind of really important. So the way I'm interpreting this, the entire section of that paragraph is the IBM documentation is suggesting that the content of a single file in Unix, slash Linux, can be interpreted in ZOS, by ZOS as the content of quote unquote a generic DASD. Okay, so if you think about a single file, okay, of Unix, okay, and then you look at it as the content of a generic DASD. So what that means is, you kind of have to. I'm not sure, whether it's needed or not, but you kind of need to look at the geometry of the virtual, DASD. What is a cylinder size, what is a track size, and so on. But basically, the content of the file is basically used to fill up the tracks and fill up the cylinders, and then you expand the cylinders to the next one, and fill up all the tracks of that cylinder, and then you expand it out to the next cylinder, and then you fill all the tracks of that cylinder. So you're basically just sequentially filling up the virtual DASD. So given that is the case, okay, given that is the case, now you're going to have to say, then what do we do about accessing the content of this quote unquote virtual DASD? From what I have read in this context, you pretty much are limited in terms of the access method. So there are certain access methods that you cannot use when you consider a file in Unix as a data set. So the two formats, the two access methods that are permissible in this case would be BSAM and QSAM. BSAM is basic sequential access method, and then QSAM is queued sequential access method. So these two are supported when you take a file in Unix and then you access it as a dataset in ZOS. Whew. Okay, so is that going to does it explain what the statement is really saying? I don't want to single out Lupe, but since Lupe asked the question, I want to make sure that I addressed the question.
Yeah, I didn't understand the whole sentence as
Mhm.
far as what it was talking about, because when I see mountable, I'm thinking of a tape. Having to mount a tape.
It's sort of like that too, because BSAM and QSAM are both supported by tape devices as well. So if you think about the content of a Unix file as the content of a tape, that also applies. That would also be a way to look at it, because on the tape, you can also use BSAM and QSAM. Is that okay?
No, that's better.
Okay.
Yeah.
Yeah, so the bottom line is the DD statement actually has to be very careful about what to assume about the internal format of the Unix file. Basically, you have to be careful about how you specify the block size, BLK size, in this case, and also the length of a logical record. So the DD statement has to be very, very specific about how to interpret the content of that Unix file. Now, if this is something that you're doing, you need to look at a file in Unix and consider that and treat it like a data set. You have to be careful, because in Unix, a line is not fixed with format. So we are not saying, okay, we are allocating 80 characters per line, and the next 80 characters will be the next line, and so on. In Unix, every line is terminated by a line feed character. So we have a So each line is terminated by a special character instead of being length delimited. So so you cannot just take any text file in a Unix environment and feed it to a job in COS and go like, oh, every line is one record, and we should be able to process that. That is not the case. Okay, so you just keep that in mind. Okay, there are text files are different. They are interpreted and formatted differently between ZOS and Unix. So just a little heads up for those of you who might run into this type of operation. All right, so now we're in section 1.5. So the question is, in this paragraph, it states a record can be personnel data about one member of a department, and a field refers to a specific portion of a record. So a record could be all the personnel information on an individual, and a field could be, for instance, a hire date. So a record could be huge because if it contains all the data, would be huge if it contains all that data, or would it break down to other records to hold stuff like performance evaluation? So this is a very, very good question, okay, because it is about asking how data is organized. When we have, so this is a great example because, we are dealing with personnel data. So some people, some employees may have a huge amount of personal data, whereas others may not have as much. Okay, one differing factor may be how long they have been hired, right? So a new hire is not going to have a whole lot of data. Okay, like okay, what are the sick leaves that has been taken? What about the performance evaluation and so on? So a new employee is not going to have a whole lot of that kind of data, whereas somebody who has worked for the state for 30 years is going to have a huge big pile of data, just because of the number of years of service. So how do we handle that sort of thing? That becomes, that's basically what this question is asking. So the answer is to think about a record as a form, and a field is a part of the form, and that is the picture that we saw earlier about the pink slip, right? But you have to remember, a pink slip is really just one piece of information related to a vehicle. What about all the registration forms, in one per year of that vehicle? That's somewhere else, right? And that is actually in a different data set. All right. So the bottom line here, okay, so let me just read what I have written here. So in the question, all data related to an employee would not be on a single physical form, but rather in separate forms. In other words, in the real world, all the paperwork related to an employee is a pile of forms. The forms are then related by the employee ID. So let me just kind of focus on this part of the discussion. All right, so and when you go to HR, okay, and you say, I want to review my performance review for the last 10 years, okay, all of those evaluation, each one being a form, which means it is a record, but all of those records are in the same file, okay, and I'm talking about a filing cabinet kind of file in this case, okay, so the HR person is going to walk up to a filing cabinet, open it up, look under your name, and then under your name there's a organizing physical thing, and then in it that would be all the performance review of past years. So that's kind of the same thing with data sets. Okay, so we're going to have a data set of performance review forms of all the employees. Okay, now you might have one data set per year just for the sake of organization, but nothing is preventing the personnel department to use a single data set for all employees, basically from the inception of that system all the way to the present. I mean, that's conceivable, okay? It's going to be a huge data set with a lot of records in it, but remember, mainframe computers are set up to handle that type of volume in terms of data processing. But in reality, more likely than not, okay, you might have one data set per year. So you have one data set of all the performance evaluation of all the employees of a particular year. So that is more likely to be the case. But the bottom line is still the same. Okay, you basically the data related to one single employee is spread across multiple data sets. One data set is specific just to store the information that is essential to each employee. So that might include first name, last name, social security number, and the employee ID. Okay, so all of these things we need to know for every single employee. So for things that are variable, okay, so this is where we are talking about here. So for things that are variable, such as every single time you take a sick leave, that should leave behind a record. So for people who have never taken a sick leave, they would not have a single record in the data set that stores only data related to sick leaves. But another employee who uses up all the sick leaves, okay, will have a lot of entries, right? So all of those entries will basically record the basic information about a sick leave, such as what day, how many hours, right, for what reason, who approved of it or who signed it off, who basically acknowledged of the sick leave, and so on and so forth. And all of those things would also have the employee ID. So the employee ID becomes quote unquote the key to identify, oh, this particular sick leave record pertains to this individual. Or if you go to the performance data set, it would also identify and go like this particular performance review record pertains to this specific employee ID. So you're using employee ID as one single identifier across multiple data sets in order to quote unquote organize all the data related to a single employee. So that would be the method that a dataset approach use to maintain audit data. Are we doing okay so far with this analogy?
Yes.
Yes.
Okay, very good. All right. Um, so in order to generate a report, okay, so at the end of the year, um, if the HR department wants to generate reports of how much sick leave is taken by each employee, that seems to be a fairly reasonable report from the HR department's perspective. So now it has to run through multiple things because it has to run through the data set that records all the sick leaves, but it also has to run through the data set that has the employee information because otherwise it wouldn't know what is the first name and last name of a particular employee because the sick leave data set only has the employee ID, to identify which employee. It doesn't have the first name, last name, address, and so on and so forth. All that stuff belongs to another data set. So now you need to access multiple data sets in order to create this report. Now, this can and still is probably still being done using simple BSAM or QSAM datasets, but the database approach is much more flexible. In other words, the HR department may have specific jobs already set up over the years so that at the end of the year they just have to tell someone from the IT department and go, okay, let's run this job and give us the printout and then we'll get it filed. Okay, and because originally everything is done using sequential access, um, it is chances are it is still sequentially accessed now. Okay, just because this has known to be working reliably, there's no reason to change it. Okay, that's kind of the mentality, and I can certainly understand why there's the mentality like that. On the other hand, if that system does not exist, okay, let's just say that there's no such thing as an existing system to report, record, and retrieve and report sick leaves, and something new has to be done to record all of this data, then a relational database is a far more flexible approach. okay? Because a relational database um, just has the ability to run queries that are very flexible. In other words, you can ask a relational database, just using an ad hoc query, which means it is not something that is precompiled. It is not coming from a library, but a database administrator can create these ad hoc queries, just by understanding what you're asking. So if you're asking how many of the sick days are coinciding with school holidays, okay, the the database administrator can create the ad hoc query like right away, okay, and run that query, and then it will give you the answer. But if you're using data sets, okay, then somebody has to create a new job, and that new job probably includes, a COBOL program that is specifically created for this particular query. So it is a little bit harder and a little bit less flexible when things are stored as data sets as opposed to a relational database. So this is a little bit of extra stuff. It did not occur to me to talk about this, but now that we have this example, I just thought that it might be helpful for those of you who will be seeing migration from dataset into relational database. A table in a relational database serves about the same purpose as a data set when we are talking about BSAM and QSAM and that type of data set. So just kind of keep that in mind, okay? Because if you run into a conversion process to convert existing data set approach into a database approach using a relational database like DB2, then understanding the terms and which term is about doing the same thing as what other term, that might come in handy. So in a relational database, there's a concept called a table that is about the same as a data set. Do we have any questions, comments, feedback, at this point? Okay. Is anyone aware of any plan to convert from using the traditional data set approach to store data into a relational database approach to store data?
Well, I I can tell you that our HR
Mm-hmm.
implemented a relational data set, I mean, a relational database in order to store the personnel information,
Mm-hmm.
but they've had nothing but issues with it because they were trying to go off of SCO's data and transfer that into the database. And SCO, I believe, is on COBOL, which is data sets. So there was a lot of problems that existed since the implementation of a database that had to be fixed
Mm-hmm.
based on the data that they were getting from SCO from their
SCO.
their information.
Okay, let me look it up. What is SCO?
State Controller's Office.
Oh, okay. So the state control office uses dataset.
COBOL, yeah.
COBOL. Well, COBOL doesn't automatically mean dataset because COBOL can actually talk to DB2 as well. It's just um, not very common. Okay, the whole reason why people are using COBOL is because they have a huge amount of data stored as datasets. If data is stored as in DB2 in a relational database to begin with, there's no reason really to use COBOL.
No, they're not on DB2 because SCO is still running the same system that they initially created way back in the day. And they've tried to convert it to a newer system and it bombed, and they had to give up the implementation of a newer system because they couldn't migrate to it.
I see. Yeah, so this kind of jives with what I talked about earlier. There's always a risk when people, try to change how data is organized, and this is exactly that example, right? Because it's an approach. They're trying to quote unquote improve things by changing from the dataset approach probably even sequential data set. Okay, if I have to guess, I'm going to guess they're still using sequential data sets like BSAM and QSAM. And when they try to change that representation into a database, relational database approach, um, they can run into issues. They can run into issues because um, I would say most of the time, the issue probably has to do with indexing the tables. That's one. And then two, all the programs that were written in COBOL before, they all have to be converted into a new program. Okay, possibly written in COBOL, but there's no reason to stay with COBOL. But the logic of all of those COBOL programs, they still need to be preserved in the new system, and that becomes the weakest point. It becomes the most brittle part of converting a system. Can you preserve all the business logic in this conversion when you're basically replacing a huge library of old programs with new programs? And during that conversion process, who's going to check, right? And how do you check that the new system is performing, exactly like the old system being replaced? So it is not impossible. It really just takes a lot of coordination, and you need to have the right type of people on the team and do it in a particular way to make it successful. It is not impossible. But it does take a lot of resources and expertise to get it done.
Well, the solution was that everything has to be entered twice, once into SCO and once into the database program. So you're doing double entry now in order for them to have the database.
That
So,
seems a little absurd to me,
yep.
because the double entry itself means that they were not able to import data from one to the other one, and that to me is that's alarming. That part is really alarming, because that would be the first thing to do, is to be able to do the conversion from data set into the relational database, double check everything, and make sure that everything that was represented in the data set is now properly represented in the database.
The only thing that they're able to do to load into the database and the SCO is the leave credit usage.
Oh
That's it.
wow. And I think the DMV had taken projects like this too in the past.
Right. Well, let me share something. We started this program where, because TMV uses a lot of paper. We send out papers
Yep.
everywhere, renewal notices, all kinds of stuff. And there's like 40 million people, about 40 million people in California. They say
Mhm.
half of those owns a car or has a driver's license. So you renew your car registration every year, and 20 million people has cars. So how are you going to be able to, because there's only 12 months in a year.
Mhm.
So we have so much. That's why we work 24/7 in our unit, because it's just too much workload.
Mhm.
So now we have this program where we're doing away with paper,
Mhm.
and where we have, let's say, Walmart is hiring commercial drivers for their trucks. So they would need to check those drivers that are applying for a job, right? Their
Mhm.
license.
Mhm.
Instead of sending them reports of their, I would say, driving record
Mhm.
in paper. So we have a contract with them where we transfer information to them electronically.
Mhm.
Okay, so we call it secure file transfer. Of course, it needs to be secured, right?
Mhm.
So what we do is, let's say they request some records, and so we receive the request, and then now we program it where we're gonna send the record to them electronically.
Mhm.
So of course, they have to open an account and make sure it's secured. Whoever is opening it on their end, because we're giving them confidential information, right?
Mhm.
So when they see it, because these are all like in data sets form, and
Mhm.
records are like coded. Sometimes you can't just read it. I mean, it's all like letters. It's
Mhm.
not like common words, right?
Right.
So but when they get it on their end, it's something that's like a user friendly
Mhm.
database where they could just read what's in the person's record.
Mhm.
So there's like a program that uh, um, built. They built the program where when we send the file to them electronically, it
Mhm.
goes to their end in a different way, so they could read it.
Okay. So basically,
So,
there's a program on the other side to
uh-huh,
decipher the records that you guys pulled out of the mainframe, so that
right,
when a human is reading the records, they can actually read it in a more readable way instead of just
right,
reading a whole bunch of characters.
right. It's like from a data set to, well, I would just say a database where they
Mhm.
could just in a database to see that person's record, and it's more readable, like understandable, and like something that they can understand.
Mhm.
It's not just a bunch of letters.
Yeah. Yeah. And then,
So,
this really just kind of occurred to me is, the conversion process is also difficult because
uh,
it is difficult to do it gradually. Because if you try to do it gradually, then you're dealing with an issue of, some stuff is converted and some stuff is not converted, and that makes things kind of difficult because um, it it changes a lot. There are a lot of moving parts. So when something breaks, it's really hard to isolate, what broke, in the conversion process. And then also the risk factor is too high too. It depends on the agency and depends on the application, but in certain cases, the risk is too high. And that is the reason why people are still, running, COBOL programs and using data sets which are very, very old um, concepts, in the 60s, okay? And that's why we are still using it, because it's just too risky, and many agencies have tried but failed to do the conversion to use, quote unquote, modern technology. And then the other side of the coin is IBM has been keeping up with their architectures as well. So even though we say, oh, you have a data set with 40 million people or 40 million records in it, and IBM just go like, oh, guess what? Don't worry, guys. We have this super duper, hardware approach to sort a data set that makes, sorting a 40 million record thing like, done, not an issue. So that makes it even harder. It removes some of the reasons to convert to a new system, because you're not gaining in terms of performance. So it's an interesting issue. It's a very interesting issue. And then the last part of the issue, and I know I'm kind of digressing here, but some of you, if you're interested in moving into the developer side of things, this is actually good news because universities are not cranking out, graduates who are prepared and equipped to work with mainframe computers. They just are not. Okay. Um, so you take any graduate from Berkeley, okay, UC Berkeley, and you would think, oh, this is one of the best, universities, not just UCs. This is one of the best universities in computer science. Okay, you take one of their graduates and you go like, okay, I would like you to work on mainframe computers and basically help us to maintain, the programs, make sure that we can, update the code so that we reflect, changes of laws and whatnot. Okay, Lupe would probably understand this part because the franchise tax board will have to change their programs annually at least to kind of take all the updates of tax laws and whatnot into consideration. So, guess what's going to happen with this graduate from UC Berkeley? That person is just going to run because there's a certain stigma associated with mainframe computers. So when you take a 20-something-year-old from straight out from Berkeley, and you say, "Oh, we would like you to work on this program," and this program has its roots from the 1960s, and we're using COBOL, and we're using the IBM mainframe computers. That person is just gonna bolt. It's just gonna run. That becomes another issue is it becomes very difficult to find replacement employees as people retire, which is which you already know because you're in this cohort. um, so that's a it's interesting because it means there really is a lot of opportunities when it comes to employment that people do not understand. Most people do not understand that there are a lot of employment opportunities related to mainframe computers.
Well, at DMV, we have like a front end group of people and the back end
Hmm.
group of people, where the front end works on uh, like the website and the the business partners,
Hmm.
but the back end works on the mainframe or COBOL, or it's mainly COBOL.
Hmm.
So they still work together, but the new hires, like from the graduates from the universities,
Hmm.
they're mostly hired on the front end side because they're programming the designing the website.
Hmm.
They're programming different databases
Hmm.
or applications that we use
Yep.
to support the mainframe, I guess.
Well, it's
But
not like they are not aware of the openings in the back end on the back end side because I'm 100% sure that you guys have openings on the back end side also, right?
right,
But the new hires, the 20 something out of Berkeley, or any CSU, any UC, any university, well, I shouldn't say any, but there are like two universities in the East Coast where they teach mainframe stuff. Um, but guess what? The East Coast also have a heavy demand on mainframe people, mainframe developers to be more specific, because there are a lot of huge financial institutions on the East Coast. So they basically soak up every person who's coming out of those universities that actually has a mainframe program. So the West Coast basically has no, we don't have any university to crank out people who know how to use mainframe computers. All of the concepts that we are talking about now and for the past few weeks, these are basically it's going to be new to any graduate from a UC or a CSU. They understand the basic concepts, but anything that is specific to IBM, like the concept of a data set, why things are allocated by cylinder and so on and so forth, they would it would be new to these people. Okay, and they have no interest either because of the stigma, because of the image. So they think about JavaScript, they think about Python. Oh, these are the latest and greatest stuff. Okay, they like it because it's glamorous. Okay, and then they look at COBOL. It's like, really? Do you want me to use a toothbrush to clean the toilet? That's kind of what they're thinking. Um, but they're not understanding that, hey, there's job security. Okay, because this stuff is not going away. There's no way it's gonna go away within a lifetime from here on, right? So it's interesting. It's just kind of interesting. All right. So moving on to CKD. Okay. So this is the question. What is a count key data? CKD. And here's a reference, footnote number 16. I think this one references Wikipedia. Is a method to organize data on a DAS-D track. Okay, so we're talking about one single track and say, okay, how do we organize data on a single track? So to pull the picture that I drew earlier, so we're only talking about one single line on a single platter. And basically we're asking, how do we store records? How do we store logical records onto that one single track? So this the second statement, basically just is a verbal description of what you saw earlier, in the picture. The amount of data that can be encoded on the track is determined by many factors, such as data density, disk head limits, rotational speed, blah blah blah, and so on. So usually we separate a track into fixed sectors, and the number of bits per sector is also fixed. So this is a very typical way of organizing data on a platter, on a single track, I should say, on a single track, on a single platter, on a hard drive. Okay, you would see this on basically any hard drive that a PC, a personal computer, would use. This type of organization allows high-level abstraction of storage on the DASD that is independent of the actual physical characteristics. Okay, so let me explain what this sentence is saying. It basically means you can go out to, okay, Fry's is no more, but you can go out to Best Buy, okay, or some online place, to get a new hard drive. You get a new hard drive back, and then you format the new hard drive to whatever file system you want to use. If you're using Windows, you're probably going to format it to NTFS. If you're using Linux, you're probably going to format it to extension 4 or extension 5 now. If you're using an Apple computer, you're going to format it to HFS, high performance file system, and so on. Okay, and once it is formatted, okay, you as an end user do not need to know a single thing about, oh, how many sectors do we have on the track, how many tracks do we have in the cylinder, and how many cylinders on the drive. You simply do not have to know anything like that. Okay, when you save a file, all you have to do is what? Control S. On an application in Microsoft Word, you just type Control S, and that's all you need to do. You don't have to understand the geometry of the hard drive. So it gives you the abstraction. This is called abstraction because you don't need to understand the details of the hardware anymore. But this approach also, it basically sacrifices input-output throughput for the ability to look at a drive as, oh, this is just a place I can store files. I don't need to understand the physical geometry of the drive at all. So the price that you're paying would be input-output throughput. Okay, how quickly can you access the content of your drive? So we talked about this a little bit earlier, because if you're dealing with an end user type of computer, having to spend another 1/8 of a second, to access the entire content of a file is no big deal. Okay, it simply is not a big deal. But when you're using a computer, using a mainframe computer to process a massive amount of data, and today, I think Jennifer just brought up, oh, the scale that we are dealing with here is we got about 40 million people in California. And assuming that we have about one vehicle per person, well, because some people have more than one cars, right? And they also have RVs, boats, and so on. So you're talking about tens of millions of vehicles, and also the records, that associated with all of these vehicles to process. So that means, efficiency becomes super important because you cannot afford that one eighth of a second to get to, certain parts of the content of a data set. So the bottom line is CKD follows the traditional IBM approach to move high-level concepts all the way down the hardware stack for performance. So what this sentence is really saying is stuff that a personal computer would do, at the application program level, because the logic to understand a Word document as a collection of XML files, and then the XML files will be parsed in this way and so on. There's a lot of overhead, there's a lot of logic involved, but all of that stuff is being done by your main processor. So your i7 processor with Intel or your AMD processor is doing all of this decoding, of the actual format of a file. What IBM is doing is exactly the opposite. Okay, we need to get to the records really fast. Oh, okay, so let's not do the processing using the central processor. Let's move that logic all the way down to the drive controller. So now you're having the drive controller to scan a track, okay, using the CKD organization. So the CKD, the K of the CKD is key. So basically a key is a unique ID that identifies a single record. So if you think about employee records, the key would be the employee ID. If you think about the record as a vehicle, record, then the key is going to be the VIN of the vehicle. So by placing the key of a record at the track format level of a DASD, now you can offload the search logic to the DASD controller. So now you can offload things so the central processor doesn't have to do all that processing. And at the same time, you're also saving a lot of input output bandwidth. Because without the concept of putting a key and having the disk controller to understand the format, what you need to do is to basically pump all the data from the DASD all the way into the CP, the central processor. So the central processor can go through all the records to search for, the record that you need. That takes a lot of resources because you need the resources to read the entire content, pump everything through the I/O channels into memory of the mainframe, and then have the central processor of the mainframe to go through all those bytes looking for a specific thing. That's a lot of work. But using CKD, sorry. So using CKD, you're allowing the hard drive controller, which is very close to the hard drive mechanism, to do all the search for you. So all you have to do is like, oh, hard drive controller, I want you to find that thing for me. And then the central processor doesn't have anything else to do. And while the drive controller is scanning through the track to look for that particular record based on the key that the central processor has sent to the drive controller, the you're not using any I/O bandwidth. Okay, so the I/O channels would not be busy during all that time. So now you basically you enhance the performance of the entire system by moving that logic all the way down to the controller. But that is made only possible by having a specific way of organizing the tracks, and that's basically what CKD is about. Okay, um, it's about moving the so on a track, CKD count basically is indicating how big a record is. That's what the count is referring to. The key is the identifier of a particular record, and then so that the drive controller would be able to do all the search and return the payload, which is the data. The data is referring to the actual data of the record um, corresponding to a particular key. So by encoding CKD, at a track level, you are basically allowing the system to be a lot more efficient when it comes to actual processing. But at the same time, this is also suitable when you're dealing with records where they can be very different. Like the size of one record can be really small, and then the size of the next record can be very large. So CKD also allows that to happen. So if you think about this, okay, let me give you an example. You can think about a performance review, okay? So for some employees, in a performance review, there may be like a few sentences, and that's it, okay? But with some other employees, you might have long paragraphs. So in using a fixed size record, you basically have to think about what is the longest performance review that is reasonable. Let's call that 4 kilobytes. Okay, but now you have to allocate 4 kilobytes per performance review, even though some of those would only use up like maybe 200 bytes. And that would not be a very efficient use of storage. But using CKD, you can actually say, oh, this one only has 400 bytes, the next one has 4 kilobytes, the next one is going to have 8 kilobytes, and then back down to 300 bytes. It allows records to have basically entirely different lengths. So that's what CKD is about. I also looked this up. I looked up the mechanism. It doesn't seem to be used much anymore, and I think that has to do with it's a mechanism that depends a lot on the geometry of the hardware. And every single time you try to use a new hard drive, you have to reformat everything to make use of this type of a method. And I think that basically make it very brittle. It's brittle to the availability of new drive technology and new drive geometry. So as a result, because semiconductor is advancing very quickly because of Moore's law. So when in the past, okay, if you have a new device coming up, new storage mass store device coming up every 5 years, okay, I'm just using that as an example, it's not too big of a deal, okay, because every 5 years you're gonna have to reformat, move the data into a new storage unit, and not too big of a deal. But these days, okay, I'm just using it as an example. Let's just say that we have new devices coming up every 6 months. Okay, so the interval between having to move data from one geometry to another geometry is a lot shorter, and that makes this approach not very attractive anymore, because you're spending a lot of time to convert the data. Remember, whenever you reorganize the data, you can run into risks of something not working anymore. So that's one. And then the second one is we just have a lot more processing power these days. So the necessity to move some of the logic down the hardware stack so that it can be performed at a lower level, that need is simply not there anymore. Okay, so we just have better ways of more resources, so that this approach is not needed anymore. Okay, so we're moving down to 1.7, and we might be just going through this one and then leave the rest to next Monday. So 1.7 is asking, can we get a visual representation of blocks, tracks, and cylinders? Or in today's world, is it better just know how many bytes each can hold? Each, I think, is representing to blocks, tracks, and cylinders can hold because of SSDs. So I dug up this thing. Okay, this is coming from a specific document, and there's a source to that one. Footnote number 17 is the source of this document in the picture. So in this picture, they didn't give you quite the size scale, but it's actually pretty big. But it's a translucent case, so you can actually see the individual platters. And the cylinders, okay, so the outermost cylinder is called cylinder 1. The innermost cylinder is cylinder, I think, 3000 something. Track 1 is the top one, and then you just count to track 15, which is the bottom one in this case. So that's how cylinders and tracks are organized. Blocks, on the other hand, are not something that is visible, because it is a block can be a portion of a track, but it can also be multiple tracks together, because you can specify a block that is longer than a track. So that's kind of a picture that might be handy. Okay, and this is the basically how things are coded by using cylinder and head to identify where the data is located, where the track is located, basically. So you first specify the cylinder, which is basically concentric cylinders from the spindle. So the cylinder identifies how far we have to move the disk head into the spindle, and then the head is specifying which platter, which identifies a single track within a cylinder. So
But
there's that. Yeah, go ahead.
when you're reading a sequential data set,
Mhm.
does it start from track 1, which is right there on top, and then goes all the way down, or
I do not know for sure, but I think from what I have read, that seemed to be implied.
okay?
Yep. So it seems to be implied that within the cylinder, you read from track 1, you read the entire content of track 1, and then you go to track 2, then you go to track 3, and so on within the cylinder. It seems to
Okay.
make sense to me. All right. So just a few more paragraphs before the end of tonight's lecture. It is true that physically an SSD has no tracks or cylinders, because an SSD is really a semiconductor device. So there's no physical things. There's no physical platter to be turning, and without anything turning, it makes no sense to talk about cylinders or tracks, because there are no platters either.
What
How,
does a SSD stand for?
oh, sorry about that. SSD stands for solid state device, solid state drive, I think. There we go. It's solid state drive. Solid state refers to the point where there are no moving parts. So within an SSD, we only have semiconductor, basically chips. There are no moving parts in an SSD. All right.
Okay.
Okay. So without any moving parts, without any platters, without any disk heads, it doesn't make any sense to talk about tracks or cylinders because those are artifacts, okay, because of the characteristics of a hard drive with platters and rotation and disk heads and so on. However, each SSD still has a native block size. So the native block size of an SSD, especially the ones using a flash memory type of technology, is native because whenever you want to update the content of an SSD, you can only update it one block at a time. And that has to do with the erasure mechanism at the semiconductor level. You can only erase one block at a time. You cannot erase individual bytes at a time. So that means there is still a native block size. Every single time you want to update the content of an SSD, you have to update it by 512 bytes, 1K byte, 2K bytes, or 4K bytes, somewhere along that line. A native block size is the smallest addressable quantum from a drive. On a flash-based SSD, a block is also the smallest quantum that can be overwritten/updated. So basically what this is saying is the concept of a block still makes sense, okay, because it's inherent to the device itself, but there's no such thing as a track nor a cylinder anymore. A flash-based SSD also has an inherent physical latency to update due to device physics. So I'm not going to go into the device physics of a flashed memory, but it suffices to basically say it does take kind of a significant amount of time to erase a block and to update the content of the block. So to reduce the apparent latency, an SSD controller may cache the content of logically contiguous tracks and cylinders in RAM on the SSD itself. In other words, you can create an artifact. Okay, this is so the concept of a track and also a cylinder is not physical, but it is an artificial construct. But it gives you it has the same reason as we want to see cylinders and tracks in an actual physical drive, which is to improve the throughput of the device. Now, this part is just me thinking that this is what's happening with high performance flash drives or SSD drives is they would still have caching mechanism. They will have mechanisms to improve the performance that will still give people the pretense of the concept of a track and also a cylinder. So things within a cylinder, if you do sequential access, they can still be much faster compared to accessing things that are not within the cylinder. So that's my guess. Okay, it is not. I could not find any actual document to support that. Oh, this is also important. Because we want to make sure that new devices are backward compatible. Now, we talked about IPL. Remember IPL? Where the first step of IPL is reading track 0, the entire content of track 0, into location 0 of physical memory. That would be the first step, right? Oh, wait, hold on a second here. If an SSD has no such concept as a track, then you cannot bootstrap using an SSD. That would not be good, right? Because you cannot just go like, oh, hard drives are slow, let's replace hard drives with SSDs. You cannot. If an SSD does not pretend to have a concept of a track, then you cannot replace a hard drive with an SSD. Okay, and this is the other reason why for backward compatibility, even though an SSD really doesn't have tracks and really doesn't have cylinders, we want it to pretend to have these things so that in the IPL process, the disk controller can still say, oh, I'm going to go to track 0 of cylinder 0 and read the content of that track into physical memory. It doesn't need to know that, hey, you're not talking to a real hard drive anymore, you're talking to an SSD. IPL doesn't need to know it. Okay, it just goes like, give me track 0 of cylinder 0. We'll start with that. And um, by pretending that we have tracks and cylinders, now we can replace gradually. Okay, we can gradually replace hard drives with SSDs in a mainframe installation without having to go through any drastic change of configuration of the system. And then we can improve the performance because SSDs are much better in many different types of operations compared to hard drives, but we don't have to pay the price of having to change configurations and go through a lot of testing process just to make sure that things still work the same way as before. All right, so that's the end of 1.7, and I think we are running out of time today, so I'm just going to continue this next Monday. How's
Okay.
that? All right. All
Thank
right.
you.
All right. Thank you. I'll see you guys next Monday.
All right. Thank you. Good
Mhm.
Good
night.
weekend.
Yep. You too. Bye.
Thank you. Bye.
Mhm.